In this lecture, we'll be discussing some advanced topics in coordination chemistry. Included in that are some biological examples of coordination compounds, such as hemoglobin. And hemoglobin is a pretty interesting biomolecule, and we'll kind of discuss some of the specifics on it. And it's something that if you go on to biochemistry, you'll study in some pretty good detail in that class. Okay, so what we'll be talking about today, listed here, we'll talk about labile versus inert to substitution, those two terms, something known as the chelate effect. We'll talk a little bit about ligand to metal and metal to ligand charge transfer, and also metal to metal charge transfer. We brought up the first two terms here. We brought those up at the end of last lecture. We'll discuss that a little bit, and then we'll get into some of the bioinorganic examples of coordination chemistry. Okay. First, we'll do a survey of some reaction types. So, first reaction type we'll talk about is substitution reactions. So this is where you get a substitution of a ligand without any change in the oxidation state to the metal or without any change of the metal itself. Right, so an example here would be we have this tetra aqua copper in the +2 state, and then we substitute 4 ammonia groups in. Okay, so we've just substituted water for ammonia. Okay, in the coordination compound, there was no change to the oxidation state of the metal. Okay, so substitution, we're just substituting ligands or a single ligand. Dissociation reactions are the next type we'll talk about. These involve a decrease of number of ligands and change the coordination number. Okay, again, there is no change in the oxidation state. So a dissociation reaction here, if we have our solid coordination compound complex ion, cobalt with 6 waters coordinated to it, and then our counter ion in the solid would be 2 chlorides. You heat that up, and then you can get a dissociation of the water. So the water will leave, in this case, and it's replaced with chlorine, and the coordination number changes. Okay, so that's called a dissociation reaction. Okay, the third reaction would be an addition reaction, and this is where the coordination number would increase. So it's kind of the opposite of a dissociation reaction. Okay, again, there's no change in the oxidation state or of the metal. Okay, so titanium tetrachloride plus 2 chloride ions go to titanium hexachloride. Okay, this would be an example of an addition reaction. We're just adding 2 more chloride ligands to that complex. And the overall charge of titanium did not change. The oxidation state didn't change. Okay, finally, we have oxidation reduction reactions, or you can think of them as electron transfer reactions. Okay, so this would be a case where the charge of the metal will change. So if we have this complex, it has a -1 overall charge. If you react it with hydrogen peroxide, the complex in this case does stay the same, but the charge now changes. It goes to neutral instead of a negative. So you're changing the oxidation state of the metal. Okay, let's quickly review some thermodynamics. Hopefully you remember most of these. Delta H, that's enthalpy. Usually in chemistry, enthalpy is just an estimation of the heat that's being transferred in a reaction. Delta S is entropy, and this is a kind of an estimation on the disorder or randomness of a system. So in our reaction, is the disorder increasing with the reaction or decreasing? And finally, delta G is the free energy. And this is what predicts the spontaneity of a reaction. For a spontaneous reaction, delta G will be negative. And a non-spontaneous reaction, delta G will be positive. Okay, and it's governed, delta G, by this expression, delta H minus T delta S. Okay, so hopefully you all remember that equation. Right. Well, that was thermodynamics. We also have kinetics to think about. And so there's kind of a distinction between the two. Spontaneity is determined by thermodynamics, so delta G determines the spontaneity. The problem is spontaneous reactions are not always fast reactions. In general chemistry, we use the example of a reaction of carbon in the diamond form going to carbon in the graphite form. And when you look at the delta G value for that process, it's a negative value, so that is spontaneous. But the reason that diamonds aren't just decaying into graphite is because of kinetics. Okay? The speed of the reaction is determined by the height of the transition state, which is known as the activation energy. And more accurately, it's depicted as delta G with this double cross symbol. That's the activation energy, or the height of the transition state. Okay. Right, so in this case, it's just a generic reaction, A going to C. Right, the change, the delta G overall for this process, right, C is lower than A. So this is going to be a negative delta G, so this is a spontaneous process. But the height of the activation energy, this barrier to overcome, right, A has to go through B before it can get to C. Right, we call this the activation energy, and this is high enough, in the cases where this is high enough, even if something is very spontaneous thermodynamically, it'll take so long to actually occur that, in a sense, the reaction doesn't happen. So that's like our example of diamonds turning to graphite. Their activation energy is so high, it's kinetically, what we refer to as being kinetically stable. Okay. We're going to introduce a couple terms, labile and inert. Okay, and these are in reference to substitution. Okay. We need to think of these in terms of half-life. So remember what a half-life is. We haven't discussed that yet. Probably not in the first two quarters. We'll be talking about that when we cover nuclear chemistry and radiation. But basically what a half-life is it's the time it takes for the reactants to decrease to half of their initial concentration. Okay. So we just define something being labile if its half-life is less than 1 minute, and something being inert if its half-life is greater than 1 minute. Okay. So these labile and inert terms are really telling us about the kinetics of the reaction, or the speed of the reaction. Stable and unstable, those are thermodynamic terms, which, if you're looking at are diamonds stable, you would take that reaction, carbon diamond going to carbon graphite. The delta G would tell you that reaction's spontaneous, so no, diamonds are not stable. They're not thermodynamically stable, but the kinetics on them is such that they are inert and they become kinetically stable. So let's see an example here. Okay, we use this reaction. So we're substituting now for NH3, we're substituting H2O. Okay, and our K value for this is 10 to the 30th, so pretty high. We can calculate the delta G from that equilibrium constant there, plug it into this equation. So the higher the K, or equilibrium constant, the more negative delta G is going to be, thus the more spontaneous it will be. Okay, so this is a very spontaneous reaction. However, this reaction takes a long time to happen. Okay, and thus this reaction is spontaneous but considered inert. Okay. So this is very similar to that reaction of diamond turning to graphite, right? They're both spontaneous but inert. Okay, another example of a redox reaction shown here. If we have cobalt and we're heating it in the presence of hydrogen peroxide with our ACAC ligand, we get it coordinated in an octahedral complex. It goes from a +2 state to a +3 state. So in this reaction, we are getting redox. Okay. And this is to illustrate, coming up, what we term the chelate effect. Okay, so the chelate effect, if we look at two reactions, okay, nickel 2+ plus 6 NH3s, and we're coordinating it now in an octahedral complex with NH3, or if we use 3 ethylene diamines, ENs, okay, we're going to get an octahedral complex where the nickel has 6 connections to nitrogens. Okay, so very similar. This is just using bidentate ligands. The K values that you see are drastically different. Okay, when you're using 6 individual NH3s, the K value is 4 times 10 to the 8th. When you use 3 ENs, it's 2 times 10 to the 18th, so orders of magnitude higher for the bidentate ligands. Okay. So if you plug those values, those K values, into that equation for delta G, right, you'd see that this reaction with the bidentate ligand is much more spontaneous. And again, they're making very, very similar complexes, right? Nickel is going to be attached to 6 nitrogens in each of these, and they're both in octahedral arrangements. So why is there a difference in spontaneity? Okay. Well, if we look at this equation for delta G, so it's based on the thermodynamic terms now, and not the equilibrium constant. If we looked at the delta H, right, the bonds nickel to NH3 or nickel to the ethylene diamine, they should be roughly about the same, the enthalpies for these, right? The bond strength should be pretty similar. So the spontaneity of this reaction has to be driven by entropy. Right? And remember, entropy is a measure of disorder, or also the number of microstates. You don't need to know this equation for this class, but the more microstates you have in a system, the higher entropy is going to be. Right? And so the more particles you have equals the more microstates equals more disorder. So when we look at this, these two reactions, let's count up the number of particles we have. So when we're coordinating with 6 NH3s, we have the same number of particles on both sides of the arrow. For the other reaction, coordinating with 3 EN groups, we're going from 4 particles on the reactants to 7 particles, right? Because we're taking those 3 bidentate ligands, connecting them to the nickel, and that's freeing 6 water molecules. So it's the freeing of those 6 water molecules that gives us an increase in the particles by doing this reaction. So that's where the increase in entropy is coming from for this reaction. So that's what's making this have a more negative delta G. So just as a general rule, multidentate ligands displace monodentate ligands. There's going to be an increase in disorder, and that's what's known as that's the definition of the chelate effect. So some common chelating agents, the really most widely used one here is EDTA, and you can see that it is one molecule that coordinates a metal at six times, 6 places. Okay, there are other ones. Okay, so you can imagine the chelate effect being very strong with something like EDTA, because it's going to displace, just one molecule of it can displace 6, if you want to think about water molecules. If this metal was just free in solution, it'll displace 6 water molecules that are around it and really increase the entropy. Okay, moving into some biological examples of transition metal elements. Okay. So there are, in our bodies, we have some trace amounts of some of these transition elements. Things like chromium, manganese, cobalt, copper, zinc, iron. Iron's probably the one that you all would probably be able to pick out just before you've taken this class to know that we have that in our bodies. But some of these other ones might be a little bit surprising. Where they're actually found in biomolecules is listed here. Vanadium, it's really not so well known yet. So that one's kind of a question mark, or at least it was when the slides were made. Okay. Cobalt is in vitamin B12, okay, and that's important in the development of red blood cells. Some other important ones, zinc, we're going to talk about the enzyme carbonic anhydrase, which is important for the CO2 elimination in the body, and as well as keeping the pH of the blood in a correct range. Okay. And then something like chromium there is involved in this glucose tolerance factor, which is important for glucose utilization. Okay. So a lot of you might see chromium in a multivitamin or in like a supplement, and this is kind of what it's used for, to help glucose utilization. Okay. Iron's the most popular one. That's in hemoglobin. It's also in something known as cytochrome C, which if you take biochemistry, you'll learn all about. And another enzyme called catalase, which removes hydrogen peroxide. Hydrogen peroxide can be very damaging. Some of the reactions in your cell sort of make it as a side product, so you need this enzyme around to be able to remove it before it damages, in particular, it damages DNA. Okay, so let's look at carbonic anhydrase first. So carbonic anhydrase is an enzyme, and it's responsible for eliminating CO2. And so what it does, I'm not going to ask you to draw out this mechanism, okay? The reaction it catalyzes is probably the thing you really want to know, as well as the fact that it's a tetrahedral zinc 2 plus compound in the active site. Okay, so what happens is you have a water molecule coordinating the zinc, as well as 3 amino acids histidines. Okay, those are inert, those don't change. What's changing is at this water molecule. So in the first step, the water molecule loses a proton and becomes a negative charge OH group. Then a CO2 can come in, and that negative charge, those electrons will attack the carbon and CO2 and form a bond. Okay, and then we have what's known as bicarbonate, which is carbon, 3 oxygens, and a hydrogen. So HCO3 is bicarbonate. Right? CO2 can come in as a gas, dissolve in solution, and now it's converted to bicarbonate, which is in liquid form. It's solubilized in a sense. The reaction can go in this direction. It can also go in the other direction. So the enzyme can also take excess bicarbonate, turn it into CO2, which then is breathed out in the lungs. The enzyme itself, what an enzyme is, I should probably explain that, is a protein that catalyzes a reaction. So all this stuff out here is just protein, atoms that are in the protein. So they're all, and proteins are just a string of amino acids. So this is amino acids out here. And this here is the active site. We have 3 histidine side chains that are coordinating our zinc, and then it's also attached to 1 water. So that's the active site. So a tetrahedral zinc complex. Right, so this is the physiology of this enzyme, which for this class you don't need to know. Just included it in case you're interested. Right, so in tissues where you're respiring, so something like your muscle when you're working out, you're going to be creating lots of CO2. Your cells are burning glucose and producing CO2 to get energy. So that CO2 can then come into your blood cell, your erythrocyte, and then combine with water in that reaction catalyzed by carbonic anhydrase and be converted to bicarbonate. Right? Then it's shuttled out here. There's this kind of fancy thing it does. It's negatively charged, so it's shuttled out, and a negatively charged chloride ion is brought in. Right, so that dissolves in the blood plasma, and then it can go transferred through the bloodstream from the muscles to the lungs. So in the lungs, the relative concentration of CO2 is very low, and so the reaction goes in reverse. Bicarbonate can come in to the blood cell. Carbonic anhydrase then does the reverse reaction and converts it back to CO2. CO2 then diffuses out of the blood cell, and out in the lungs, you can breathe it out. Okay. Okay, the next biomolecule is hemoglobin. Okay. And this is one of the more widely studied biomolecules. It was one of the first biomolecules that was actually studied. Because it is such a large component of blood. It makes up about 35% of red blood cells. So it's there in a huge amount, and it was easily isolated, so it was a good first molecule to study. Okay, each hemoglobin can bind 4 molecules of oxygen. What hemoglobin is, it's a protein that has 4 copies of itself stuck together in a complex. So each of these different colored ribbon structures is essentially the same sequence. There are alpha and beta subunits. So 2 of them are identical and 2 of them are identical, and then they're slightly different than each other. But you can just think of it as 4 copies bound together in what's known as a tetramer. 4-protein complex. Each of the subunits has a heme group, and that's what we're really going to be focusing on with hemoglobin. And that's one of the reasons why it has its name, hemoglobin. Heme, that heme part stands for the heme it has, cofactor. And globin just means a globular or round kind of ball-shaped protein. So the heme group, if we look closer at that, it's what's known as a porphyrin ring. So this carbon structure, ring structure with 4 nitrogens in the middle is a porphyrin. You won't have to draw this, so don't worry about drawing this. It's pretty complex. The important part is the middle. In the very center, we have an iron. Okay, that iron in this drawing is in the +2 state, but it can change. And it's bound to these 4 nitrogens. So that makes sort of a square planar arrangement, just with respect to the nitrogens. Okay, it's also bound to, beneath this, it's bound to a nitrogen that's in an amino acid histidine on the bottom. And then on top, it binds O2, oxygen. Okay, so hemoglobin is responsible for binding oxygen and transporting that oxygen from the lungs to the tissue. Okay, so its job sounds simple, but when you think about it, this protein has to be able to bind oxygen in the lungs and then release it in the tissues. So it has to be able to do both bind and release. So it has a kind of unique way of doing this. If we look at the deoxygenated form, so without oxygen bound, the iron in that heme group is not really in the plane. So it's kind of dome shape or puckered. Okay? And when it binds oxygen, that oxygen, you can think of it as kind of pulling that iron back, and the iron then becomes in the plane of the heme. Right, so here the drawing says domed for the oxygen free and planar for the oxygen bound. Okay. Well, iron is bound to this histidine on the other side, so when that iron gets pulled forward slightly, it's pulling on that histidine, which then pulls on the rest of the protein. And that pulling of the protein gives the conformational change of the protein, which then signals to the other subunits to be able to bind oxygen more tightly. Okay. When deoxygenated, the iron has an oxidation state of +2. When oxygen binds, iron is oxidized to iron 3. So that's another difference. The iron goes from +2 to +3. And if you think about the color of hemoglobin, when you have deoxyhemoglobin, so without oxygen, right? You think about the blood in your veins coming back to your heart, looks kind of bluish, right? Because there's little oxygen in it. And that's because you have an iron 2, which is D6, and the geometry of it is sort of what's referred to as pseudo-square pyramidal, which we can kind of estimate the crystal field as the same as a square planar would be. So if we fill this in, right, with 6 electrons, we'd have these 3 orbitals filled. Then when it absorbs light, it's going from this energy state to the next highest one. So it's absorbing a pretty low energy, 580 nanometers. So it has fairly small splitting, and that's what gives you that purplish or sort of bluish color. When oxygen is bound to hemoglobin, right, we're now in iron 3, which is a D5. You also get the coordination is octahedral, So we write out our coordination as octahedral, that pattern. Okay, this is a low spin complex, and we put all 5 electrons down here. One electron can bounce up to the next energy level. This splitting, though, because it's octahedral, even though it's low spin, it's octahedral, it is higher in energy than this splitting. Okay, so it's absorbing light that's higher in energy. It goes from 580 to 480. So the color that it's giving off is a brighter red color. Okay, so that's a way we can use coordination chemistry to explain the differences in the color of oxygenated blood versus deoxygenated blood. So the ability of hemoglobin to bind oxygen depends on the number of oxygens that are already coordinated to other heme groups in the molecule. So once one oxygen binds to a hemoglobin, let's say just in this red subunit, the other 3 subunits now bind bind oxygen stronger, because the equilibrium constant for the other 3 subunits changes. So this cooperativity effect of binding one subunit that increases the affinity for the subunit at the other sites, that's what's known as an allosteric effect. And again, if you take biochemistry, you're going to talk about that quite a bit. So our reaction here, hemoglobin plus oxygen goes to oxygen-bound hemoglobin, and it's in equilibrium. So when you're in the lungs, there's an excess of O2 that you're breathing in. So that's, if you use Le Chatelier's principle, right, you have an excess of this, so you're kind of pushing the reaction this way towards the oxygen-bound hemoglobin. So you get more bound hemoglobin. When that hemoglobin with bound oxygen reaches cells and tissues, the environment's different, right? It's going to have much less oxygen in it. So that shifts the equilibrium. So instead of having an excess of this, you sort of pulled all of that away, and now that shifts the equilibrium this way, right, backwards. And O2 is then released where it is needed. Okay. There are some ligands that can compete with O2. One of the most dangerous ones is carbon monoxide. Okay. It binds with iron much stronger than O2 does, actually. Okay. And that causes hemoglobin to be unable to transfer oxygen. So binding of carbon monoxide, and it acts just like oxygen when it does that. So if carbon monoxide binds at one site, it's going to make the other sites have a higher affinity for oxygen, which you might think is good. But the problem is it binds so strong that it makes it unable to release the oxygen where it's needed. So in a sense, if you have carbon monoxide poisoning, it's kind of like you're suffocating even when you're breathing and there's oxygen around, because your hemoglobin can't work correctly. Right? And as little as 1% carbon monoxide will convert that hemoglobin to the carboxy hemoglobin and lead to loss of consciousness and death. So it only a very small amount of carbon monoxide can do that. Okay. Another something that can compete with O2 is cyanide. Okay. This mainly affects cytochrome hemes in electron transport chain, though, and not necessarily the heme in hemoglobin. Just a quick note, there's 400 parts per million concentration of carbon monoxide in cigarette smoke. That ties up about 6% of the hemoglobin in your bloodstream. So that seems like a small amount, but that increased stress plays a pretty big role on the heart, because the heart has to work harder to compensate for that. And that's, for regular smokers, that's 6% difference all the time. So the heart is just doing that extra work. And that's one of the reasons to believe why smokers are at higher risk for heart attacks. If we look at the shape of the binding of O2 versus CO, you can see that O2, when it binds, is kind of this angle, and carbon monoxide is linear. Okay, that's one of the reasons why carbon monoxide binds 10 to the 5 times better than O2, because it seems to fit in there better. Okay, and that's a huge a huge number to be when the enzyme's designed to carry oxygen and it's binding carbon monoxide that much better. It's kind of unusual, right? Okay. This kinked binding topology actually does, sorry, I misspoke earlier there. It actually favors oxygen, so about 100-fold. So the binding constant doesn't take that into account. So when you take that into account, the binding of carbon monoxide is actually only about 230-fold stronger than O2, right? And so that's, the binding site is designed to fit this kinked binding of O2 better than this linear binding of CO. Okay? And that's one of the ways hemoglobin has adapted to try to neutralize this greatly increased binding of CO to the heme group over oxygen. But it still is 230-fold stronger than oxygen. Okay, the next biomolecule we'll look at is one that we've talked about, made reference to in the class, is cisplatin. And remember, that's where you have a platinum in a square planar arrangement, and you have chlorines on one side and NH3 groups on the other side. Okay, the platinum is in the +2 oxidation state. That makes it a D8. Again, square planar. This is used as an anti-cancer drug, and we'll talk about just basics of how that works. Okay, it binds to the DNA, causes a kink in the DNA, which induces apoptosis. So if we look at this, our DNA, double-stranded DNA shown here, the G side chain, or I should say base, because it's DNA, the guanine base is shown here. That's the one that cisplatin is preferentially binding to. So it will bind, and it binds via those chlorines. So it can get rid of the chlorines and bind to the guanines, and where there's guanines fairly close together. Okay, and by doing this, it makes what's known as a crosslink, an intrastrand crosslink. And you can think of this just kind of mucking up the structure of the DNA. Okay, you don't need to know this detail for this class, but it's the N7 position of guanine. So it's primarily adjacent to the 1,2 intrastrand adducts. Don't need to know that for this class. What it does do, though, is it creates a kink in the DNA, which then ultimately leads to apoptosis. And apoptosis, what that means is programmed cell death. Okay, you might think that doesn't sound good, but where this is really effective are in cells that are dividing rapidly. Okay, if you put this in it kind of mucks up the DNA, creates kinks in the DNA. Machinery, we have machinery in the cells that tries to repair damaged DNA, and it'll come to this sort of a kink, and it won't be able to repair that. And that will signal, okay, this cell, the DNA damage is beyond repair, so let's destroy this cell. Okay, again, doesn't sound like a good thing, but when you think about it, cancer cells are dividing much more quickly than a regular cell. And so that's where it has a much bigger effect on cancer cells than normal cells. But some of the side effects that chemotherapy has is due to the fact that it's also acting on your normal cells as well. Okay. Here's a good video if you want to watch cisplatin in action, so the link's there. Sulfur-containing amino acids can actually cause side effects with cisplatin, and that's because we have softer sulfur atoms that combine with the softer platinum in cisplatin, and that just causes some of the side effects with the drug. There are other analogous chemotherapy drugs that use a similar pattern as cisplatin. So here's cisplatin. We have, this example is carboplatin, where you have that same two NH3 groups on platinum, and then you have this bigger, larger molecule out here. And then the oxaliplatin is shown here, where you have sort of complicated structures on both sides. And all of them are in the cis conformation. Again, that's important because you want it in the cis conformation to be able to make those kinks in DNA. Okay. These two forms, because they're replacing the chlorides with these other bigger pieces, make them less reactive, and therefore they have less side effects. So the last biomolecule we'll talk about are gadolinium contrast agents. Okay. And what a contrast agent is, it's something that its job is to shorten the thing that's known as a relaxation time of hydrogens in neighboring water molecules. Okay. And what you're using that for is to visualize it on an MRI, so a magnetic resonance imaging. Okay. Gadolinium, and we'll see, we'll go through this and see why this is so good at being a contrast agent, but it's toxic. Okay, so just free gadolinium by itself is toxic, so you have to chelate it. And this is just some examples of gadolinium contrast agents that are available. And you'll notice that these chelating agents are pretty complex, and in fact, they have, up until this point in this class, we've only talked about coordination compounds that have 4 or 6 coordination sites or coordination numbers, and you can see here that these actually have more. So their actual geometry around the gadolinium is more complex. It's different. It's above octahedral. If you're curious about MRI or the analogous technique that you use in chemistry and research, which is called NMR, nuclear magnetic resonance, this little figure here explains it in some pretty easy to understand terms, so you can go through that if you're interested. For this class, it's not going to be super important to know. Just kind of understand gadolinium and why it's important as a contrast agent. Okay, so typically, gadolinium 3+ is used in these contrast agents. And when you do the electron configuration with gadolinium 3+, you see that it has 7 unpaired electrons. Okay. What that gives is a very large magnetic moment. Right? And that's that large magnetic moment that is good for contrast agents. Okay. Also has high aqueous solubility, which is good because contrast agents need to be delivered in an IV, so they need to be water soluble. Okay, the complex surrounding gadolinium must contain the gadolinium, obviously, but also have open coordination sites for other exchangeable ligands. Okay, and those other exchangeable ligands will be water molecules. And then the high relaxivity, that might not make a whole lot of sense to you, and it's probably okay if it doesn't in this class, but gadolinium shortens the proton relaxation time by a technical term here, a lot. Okay, so it's the relaxation times are what you're measuring in NMR or MRI, and by shortening them, you can be able to get some contrast between tissues in blood or different types of tissues. Okay, so the water going on and off of the contrast agents has to be fast, so there's a fast exchange rate. Okay, so water bouncing on and off. The complex has to be stable to substitution, right, or inert, that term inert, because we don't want other metals to substitute out the gadolinium. One, because the gadolinium free by itself could be toxic, and two, because these other metals aren't going to give you the relaxation you need. Okay. Protein binding, that complex, the gadolinium complex, when it's bound to a protein, which there are tons of protein in the blood, like serum albumin, the rotational tumbling of the complex is going to be slowed, right? Because it's on a bigger molecule, it's going to be rolling around slower. And when that happens, that increases the relaxivity of that complex, because those 7 unpaired electrons are going to create a strong magnetic field, local magnetic field there, and that's going to fluctuate at the rate at which the complex is tumbling in solution. So if you slow down the tumbling, that magnetic moment isn't going to fluctuate as much, and that's just going to make it a stronger contrast agent. So protein binding is good. Okay. And I think the other parts here are just kind of over the detail we need in this class. Okay. So that is all I have for the biological applications. Next time we will be doing an exam, so just a reminder that the first exam is coming up. If you do have questions in class, or you can also email me as well. And good luck on the exam.